So our statement reads, a sphere of linear magnetic material is placed in an otherwise uniform magnetic field B naught. Find the new field inside the sphere. All right. So we've kind of done this before a few questions back with the whole potentials and separation of variables. So we'll emulate that again. Here we have W in, W out, and the boundary conditions. Of course, now we have to be careful with the second boundary condition multiplying by mu naught since we're outside of the material, and mu when we're inside the material, due to the different susceptibilities. Okay, so if we consider the perspective of the potential again, we see that for large r, we want b of r theta goes to b naught, which is equal to b naught z hat. Okay, makes sense. We're large, we're away from everything. Now with the auxiliary field h, we know that that's equal to 1 over mu naught b, so that would imply that h goes to 1 over mu naught b naught z hat, and hence the w is equal to, or the potential is equal to negative, because remember negative gradient, is equal to negative 1 over mu naught b naught z, of course, but we can break z down into r cosine theta, so you're good there. All right, so by applying boundary condition 2, we see that mu naught equals, in the parentheses, we would shove that case through due to the Lagrange polynomial. On the outside, we have b naught cosine theta. And then on the inside, we see that we have BL over R. For the inside, we see that. And then for the outside, we see that we have BL over RL plus 2. Same setup we've had previously. We understand what's going on. So now we just need to use the mechanics of chapter 3 again. And for L not equal to 1, again, because we have a cosine there, we're going to end up having to play, mix match and set everything equal to one another. This yields BL equal to R raised to 2L plus 1 AL. Again, we've seen this before, so we just plug that in and we solve. And therefore, we prove that AL is equal to 0 for L not equal to 1. Now, for the case L equal to 1, we have A1R is equal to negative 1 over mu naught B naught R plus B1 over R squared. And 2 then yields B naught plus 2 mu naught B1 over R cubed plus mu A1 equals 0. So we set the two equal to each other and solve a couple of nonlinear equations, so be careful. And what we see here is that A1 is equal to negative 3 B naught over 2 mu naught plus mu. So the potential is, well, now we plug everything in, and we see that we have negative 3 B naught over 2 mu naught plus mu R cosine theta, which goes back to Z. And if we take the gradient, negative gradient of course, we see that Hn goes to 3 B naught over 2 mu naught plus mu. And therefore B equaling mu H naught, we just get another factor of mu. But let's recall that mu is equal to 1 plus chi m, so we're able to simplify through. We've seen again this, we have seen this before with the electrostatic case and polarization, so don't be alarmed when you see it, but be aware of it. So since we've seen it before, we'll use what we know from before as well. So as in chapter 4, B naught magnetizes a sphere, M naught equal chi m H naught, and then plug it through. And then in turn, this magnetization produces a field within the sphere, so we get this reiterative loop back and forth, back and forth. Okay, so what does this converge to? So we find B1, okay, and we'll just let kappa equal chi m over 1 plus chi m, so we don't have to keep tagging it along. And now we see that B1 magnetizes the sphere an additional amount, M1, and so on and so forth. So if we plug this through and we see that we get this back and forth, what we see here is that B is equal to B naught plus B1 plus B2, dot, dot, dot. And so we see that we keep getting this factor of 2 kappa 3. So we just, add up whatever term we're on, square it, cube it, etc. But we see that this is a series expression, and we know it's going to converge because it's a geometric series. And we say now that with the geometric representation, we can do 1 over kappa, blah, blah, blah. That goes back from calculus roots. And now we're able to simplify it through with what is 1 plus 1 minus 2 kappa over 3 in terms of chi m. And we'll just, let the math be the math. And we see here that that's equal to, if we divide through by 3, we get 1 over chi m plus 1 over chi m divided by 3, B naught. So that's equal to the total field. Again, we've seen this result before with the polarization in the field, so it's not unheard of, but the analogous continues to build on one another.